And here we're going to capture a fine-grained per frame trace out of the graph dispatcher. First off, let's see what we're doing here. Set up some interfaces and so on. And as you can see, we're pounding along at about 22 Mbps. So this is a high performance kind of case where we'll probably see some pretty interesting thing down at the detail level. And this turns on the fine-grained event logging. If we look again, it will have clearly stopped itself because at 22 Mbps it doesn't take a long time to fill the event log buffer. And in fact, we'll save off 8 million events. Here we have the event data we just captured displayed in the G2 graphical event viewer. There's fairly good documentation of how to build the event viewer and so on, so we won't go there for the moment. But you can see from the time line at the bottom that we captured nearly 2 seconds of 22 Mbps traffic being processed by 2 worker threads. The default track actually is thread 0, and what you'll see these are timer wheel expiration tick-offs about every 10 milliseconds. Any rate, so let's see at a finer grain what these data look like, and we'll end up having to zoom in quite a fair amount before we start seeing trees instead of the entire forest. Notice that these are, this is about 10 millisecond kind of time scale. If we turn the event display on by hitting the E button, you'll see again it's a little bit dense to look at, so let's zoom in again. Now these are in the right corner. What we've captured out of the graph dispatcher is call and return frame sizes for each of the graph nodes. So if you look at frame 1, DPDK input getting 60 frames in that on that thread. And why don't we actually just clear the set of events so it's more clear. These are the DPDK input guys, and you'll see that they're running at a vector size of plus or minus 60 in this case. And if we look at the period, you'll see that the graph dispatch loop time is 5.5 microseconds, during which 60 packets are processed start to finish. So you can do the math of how many PPS that is. Now, there's a pretty interesting thing that one can do, which is to look for anomalies in the data. If we hit the anomaly button and tell it, event code 1 here, meaning the guys we've displayed here, it'll start searching for places where, how would you say it, where we exceed the threshold value of 131 elements in the input or output vector from the given graph node. And in this case, you'll see, okay, there's 132, so this is somewhat of an anomaly. Now, if we zoom out a little bit, what you're going to see is kind of an interesting break in the pattern we've been seeing. You'll see here, it'll be running at, okay, 88, yada, 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 88, 88, 56. Now, that ended up right there causing a bit of an anomaly. This is actually pretty interesting in that if you can figure out what's going on in this little Nixon gap of 7 microseconds as opposed to the prevailing circuit time of around, well, I don't know, I guess there the prevailing input circuit rate was about the same. At any rate, you can often figure out some pretty interesting things by looking for anomalously large vector sizes. One of the other reasons for doing this, this particular little VOD, is to show you that, okay, so for whatever reason, the circuit time increased a little bit. We piled up a bunch more vectors. And if you look here, you'll see that the vector size is starting to come down again to the equilibrium value. This is a really nice data set that demonstrates first of all, some level of fine-grained chaotic behavior, which isn't really surprising. I mean, this is a dynamic, VBP is a dynamic system. It's not real surprising that there are anomalies, but this data set goes a long way towards proving the thing that I've said many times in other videos and to anyone who will ask, which is that the graph dispatcher equilibrium frame size is actually, you know, a stable equilibrium, that if things increase for whatever reason, they pick right up again. Now here's another, just by eyeball, we get a fairly small vector, and then one of more modest size again. So at the fine grain level, the world is a little bit of a mess. You would have expected this. On the other hand, you know, we have some nice tools in the visualization arena to just go find these anomalies. In fact, if you hit next, it'll start looking again. And oh, this is a better one where you'll see, you know, okay, so there's 16 microseconds. Right here, we were running at an input rate of, you know, call it 60, and now here we'll go to 150. Now, you know, again, the good thing is, okay, so we've taken a little bit of a break from packet processing for whatever reason, and, you know, the vector size does an excursion to 150, and then, you know, by here, okay, so it's saying reasonably constant for a little while. Let's deselect that. But now, after a couple frames at that size, it starts to melt back. And after a while, you notice, of course, it didn't drop anything at that rate. The ring size, the maximum vector size is 256. I wouldn't have expected to see any packet drops as a result, but you do see the anomaly detector finding some really interesting stuff. At any rate, hope that was interesting.